Good morning. I'm Mike KASTURA, and I'm from Magnum Products. So we're going to get right into this because we got a bunch of slides. So as I said, I'm the Director of Product Development for Magnum Products, and here to talk to you a little bit about Thermoset additive manufacturing this morning. Just a real quick about Magnum Products. We are a fluid movement machine company. We tailor different units and machinery for precise meter and mixing. Our company is split up into four major buckets: composite application equipment, adhesives equipment, automated solutions, and then additive manufacturing. Within the composite applications, we have traditional gel wet out type machines, some higher end injection and closed molding machines. And then adhesives and sealants, we have the things you would kind of think through and think we would have: adhesives and putty systems and single component type machinery. In the automated division, we have filament winders, impregnators, flat panel machines, anything from 2 to 3 to 4 different 4-axis filament winders. And then the additive manufacturing division has two different product offerings: a 4 by 8 foot by 4 foot machine that's 1.3 meters by 2.6 by 1.3 meters, and then a larger one that was sort of our proof of concept with Oak Ridge National Laboratories. And in the middle there you can see it's operated by Siemens Controls, customized Siemens control package. So before we get started, I really just want to level set. We're talking about thermosets and not thermoplastics, right? So if you think through what a thermoplastic is, it's the process of additive manufacturing there for large scale. Predominantly is you're melting the plastic onto another piece of plastic that's still warm. Whereas in thermosets, it's a chemical bond that's happening. And I liken this to butter versus pancakes, because butter you can heat up and it goes back to the same state, whereas pancakes you can't really unmelt. To further illustrate this, it's really as the pellets are going in on your left, for a thermoplastic, you're putting pellets in a heated head, and the peak exotherm is at deposition, and then the product starts to cool. In thermosets, you're adding two chemicals or two different materials. It's going down cool, and your peak exotherm, the red, is some time after deposition. To further illustrate that, this is a thermal imaging of one of our processes where you can see the material is going down in this purple color, and you'll see a wave of heat following it. And this is sped up quite a bit, obviously, but you can see it, that wave of heat that follows the deposition. So why the thermal sets? Why start going into this? Well, it is actually a more energy efficient system. So rather, you're not having to use heaters to heat up or dry out your pellets. The DOE, Department of Energy, did a study at Oak Ridge National Laboratories and found that we were 5 times more energy efficient than any other machine that they had tested, which included a large-scale thermoplastic machine. But that's really not the most exciting parts. One of the biggest advantages of using thermosets is a stronger Z-layer strength. So the Z-layer meaning the bead-to-bead interaction. And again, this comes from, it's a chemical reaction, not a thermal reaction. Some test data that has the orange here represents 20% glass-filled ABS versus base material from pollen, PRD. And you can see the tensile retention strength properties is much lower in the orange, the thermoplastic, than it is in the thermal sets. It really comes down to that at this molecular level, you're entangling the fibers, you're entangling the different molecules. Thermosets are also more heat tolerant. You have a higher TG in most cases with thermal sets. You also have a reduction in thermal expansion. So when you use the what the product that you're printing, and we've done mostly molds to start with. As you're using the mold, it heats up. As the mold heats up, you start to get expansion, and this has been a big problem with thermosets over the decades we've been using them. With thermoplastics, you're getting less of that. And so this graph illustrates in the orange is the Y direction expansion versus the X direction. In the top two examples, you have this really short expansion in the X direction and a longer expansion in the Y direction. In many cases, 10 times more. And that's really because as you're printing, the fibers that are contained inside of the material are lining up in that X direction, and they're holding back that print. And they don't do that in the Y direction, and so you get this enormous distribution of change in your print or in your mold, whatever it is. In thermosets, that retention is much higher because of the entanglement and because you're using a chemical reaction. So we're getting closer to isotropic expansion, and we do have a few other experimental materials we're working with that hopes to get to isotropic expansion. Because there's this chemical bond, you have what we're calling an open layer time, meaning you don't have to come back and put your material back at a time frame in the same way you do with thermoplastics. In thermoplastics, you're melting that material, and you're using that heat, that melting process to put those two pieces back together. In many cases, you have a limited amount of time to come back to that previous layer. Otherwise, you lose the print because there is no retention between those layers. With thermosets, you don't have that, so you can literally join two pieces together once you've printed them with the same material. And I have some real-world examples here in a minute. It also allows you to easily modify or repair a mold or whatever you're working with. If you want a version 2 of a part, you quite literally can mill out or break out that part, reapply the same material, and then go back to the CNC machine. It also allows you to start and stop in the middle of a print, meaning you can quite literally print part of your print, go home for the night, and come back the next day and continue printing and still have the same characteristics. And again, I'm going to show you an example of that in a minute here. The open layer time also allows you, as well as it being a thermoset to begin with, allows you to have different finishing products put on or the same finishing products that you may be using in your traditional process already. Because you're putting a thermoset, a lot of time your finishing coats are thermoset, and you're putting that on to your mold. Well, when you're using a thermoplastic mold, a lot of times you'll see delamination because the thermoplastic is expanding because of that CLTE is much different than your thermoset. So if you're heating that mold up or that part up, you will see or could see delamination, whereas you don't see that in the thermosets. As well as just easier to apply to a thermoset. The last advantage I have here is you're able to print in multiple parts. In the bottom left picture, we actually printed all 3 of those parts at the same time. Each 1 layer, 2 layer, each one of those layers as it came up. And as you can see, 2 of the 3 are a mirror image, but the third is a completely different shape. And although thermosets do print slower, you can do multiple parts at the same time and gain efficiencies. You also gain efficiencies later because they're much easier to mill than thermoplastics. You're also able to pick or index. In the video, you can see there's a square that's being indexed into the print. And the machine actually goes over, grabs a piece of foam, and drops it into the part, continues to print, and actually prints over top of it. So now if you're thinking about, say, lightweighting a part, you can drop a piece into it, and you may not need the arm to do it. You could physically put it in. Or if you wanted to put in heating channels or cooling channels or sensors to check the degradation of the tool, or sensors to see what temperatures you're at. It's very easy to do with this. Again, it goes back to this open layer time, that you're not under this time crunch to get your layers back on top of each other. And those layers can be tailored whether you want them to cure 1 layer deep or 7 layers deep. So currently there are 5 different materials available. They're all available from Polymers. Their booth is down here in this hall in M12, I believe. We've done material applications on 2 of the materials so far, the PRD 520 and the PRD, I always forget the number, the 1632, which is, so one is carbon fiber based and one is glass filled. But what's really exciting is in the middle section there, the middle material, you can see on the bottom the CLT is very, very small, and this is approaching aluminum in the sense of the expansion rates that you're seeing in tooling, as well as the TG, the temperatures at which they you can produce to. So we're at the low end of autoclave tooling and have plans to be into full aerospace autoclave tooling with the pressures. So this is an example of one of the molds we've produced. This was an infusion tool. This print was done with the PRD 1520, and the print time did take 72 hours. So that's the actual print time that we were laying down material. But the actual time this took was about 3.5 weeks, because this was printed with in coordination with Oak Ridge National Laboratory. This is the first machine that we put, and they've helped collaborate with us. But in the middle of it, the operators were put into COVID protocol, and they literally could not get in the building for 10 days. And right about here, actually, it's right in the middle of it, we had to stop the print, and we came back 10 days later and starting to print it. Now that was not planned, but the print still worked. You can also see the lights kind of going off and on there. Now some of the times they were working in the middle of the night and the lights were going off, but other times the first couple days they printed and they went home and they came back and printed. That was planned, but the 10-day COVID was not planned. And this print did end up being just around 1,100 pounds. The dimensions on this is it's 10 feet deep into the screen, about 3 feet wide, and about 2.5 feet tall. So this is a case study. I'm going to kind of break this one down a little bit, of a thermoforming mold for a shower pan. This was also printed with the 1520. You can see in the bottom left, we started this print with a sparse print. So there's a grid work here of about 1-inch crosses, and that was done so that we could lightweight the tool. We were also creating a hollow base for this because it is a thermal forming, so we're going to add a vacuum system to this, as I'll show you in here. So it started sparse. As it started getting closer to the surface of the mold, we started closing those squares until it got to a solid surface, and then you can see the print here in the lower right. And that total time of print time at this time was 27 hours, and this is only printing around 8 pounds an hour, and we've far surpassed that now. We've doubled that in many cases, but we're able to print much faster now. But at this time, we were going a little bit slower. So then that mold was taken to a CNC and was done on a 5-axis machine here. That took 16 hours. And again, as I mentioned before, the milling on thermosets is typically faster than the printing. On thermoplastics, it's just the opposite, because in many cases, as you're milling, you're heating up whatever material you're milling, and in many cases, the thermoplastic can't withstand that heat. You'll quite literally melt it again, like the butter. And so you have to go much slower on that. And in many cases, milling in a thermoplastic is anywhere from 2 to 5 times what it took to print it. And so if you think about this, the timeline of going from a print, from a CAD file or an idea all the way to the end product, there's 9 to 11 steps that you have to take to get there. And printing and milling is just a couple of them, and you can offset those by different efficiencies. And our efficiency is that you can mill faster and it's easy to mill. So after it was done milled, we took it to the finishing shop, and they fiberglassed the bottom to seal the bottom of it because it did start with sparse. They added ports for the vacuum and drilled some holes and built a frame, and that took 16 hours. So then this is at Oak Ridge National Laboratories where some of the trials were held. Using ABS sheets of plastic, the sheets go in and they're heated at 163 degrees C, and they come out. And the test was done with 20 sheets continuously with a 2-minute cycle time. And this is a quick video of it. On the left is the sheet coming out of the heat, and I'm going to start the other side. And the other side is the thermal imaging of it. And so the sheet comes down, vacuum's applied, and it kind of sucks it down on there, and you can see it's now formed. The one on the right now, that sheet comes out really hot. Again, it gets sucked down, and you can see it cooling. Now this is sped up a little bit on the right-hand side, and you'll see it pop right off there in a second. It pops off, and cycle continues. Again, every 2 minutes that goes through, and the mold is still in use and still being able to be used. So to complete that case study, it was found that this is a valuable way to produce a mold, and the total time took 59 hours. And you can see we did measure temperature over the period of the trials, and no part of it ever reached above 100 C. As I mentioned earlier, you're able to do multiple parts at once. So this was a mold that we were an ACE finalist at for Chemex. The mold here is a traditional open fiberglass mold for a wheel well. That's a wheel well of a mobile home. And it was printed in 2 parts, as you can see both in the illustration from the slicing software in the bottom. So the first couple layers are printed. The flange is done. The walls of the well can keep going up. The walls of the well were finished. Let that start to cure. We picked up the flange, set it on top of the well. We did add a little bit of weight to it to kind of help push down and keep the flange there. And it was able to cure into one piece. And effectively, we printed a 90-degree angle with no support structure, therefore saving weight, saving cost, and really showcasing that a traditional mold can be made very quickly. This was a thermoform compression mold. This was a block was just printed quickly. It was milled with 5,000 step over in the CNC machine, and was tested in a 5-ton press. And you can see in the bottom right where there's a red circle there, some heating channels were placed into this mold during the print, as we showed the video of foam going, and this one copper tubes were added to it. Water at 82 C was added to warm the mold. The mold surface actually saw about 38, and we used pre-preg carbon, and this is a gas cap. And that was again cycled. I think the cycle time on that was around 3 minutes. And we are able to finish, as I mentioned earlier, one of the advantages of being able to use finishing coats of Thermosets. Here's 2 molds that we've done for different partners where we finished them and achieved Class A finish. So these were printed, they were milled, they were ground, sanded down to 600 grit, they were coated and sealed down to 3,000 grits, and then they were polished down to a Class A surface finish. So I mentioned that we have a carbon fiber material. This is that, and it's material that we're finishing up some of the application science on right now. This is a high temperature, low shrink material. And as you can see, this was just kind of a close-up of a quick print we did. It's very, very void free. The print on the left was done with a 1 millimeter nozzle, so the ridges on the top are 1 millimeter. The print that's going on the right-hand side, that's a 3 millimeter nozzle. So we are able to adjust the nozzle sizes, and when we adjust nozzle sizes, our output, our volumetric output is the same. We just speed up the machine. So there's that. So in summary, large-scale thermoplastics, they have very large strength, or their strength is in because of the chemical bond. They're very heat tolerant because we're using thermosets. One of the key advantages is here this open layer time. It allows you to do a lot of different things like picking and placing items into a part, joining parts together, being able to stop the part while you print and go home, have a sandwich, get COVID. Because you're using thermosets, the finishing is very easy. In many cases, you can you can just mill it and sand it, and it's good, as in those carbon fiber gas caps, or you can apply and get a Class A finish. And there's a lot of different process efficiencies, like printing it dual parts or multiple parts at once. And we have shown that through case studies that this is viable, and we have used them in production. And it does save time and cost. In many cases, the time to produce, I should have said the shower pan mold took 6 weeks traditionally to make. We made it in 6 days. We've made some prints recently for a customer. It took them 6 weeks to get an aluminum mold. They printed and milled it in 1 day. So the time and cost savings is large. So some of the research that has been done with Oak Ridge at National Laboratories at the MDF Center in Knoxville, Tennessee, and just wanted to say thank you to them. Thank you to Tolerant, our material partner, and that's it. So that's my contact information, and looks like I tried to go through that quickly in case there was any questions. I have about 2 minutes if there's any questions. Okay. Well, if you have any questions, I guess I'll be in the back if anybody has anything else. I appreciate your time. Thank you.